Okay, so let me talk about this cyclic groups. See, let me just tell you in general about the cyclic groups and all the other groups which comes after this, like inclined force group, that additive sum group, and that all this group. So the only common thing is here is nothing but it will be in a manner. So like according to a cycle, will be writing this. So which means suppose whatever the given elements they have given. So if I add two terms, that should give me the sum as third term. For example, 1, 2, 3 is there. If I add 1 and 2, it should give me 3 like that. So if I write 1, 2, 3, now if I suppose I add 2 and 3, I should get 5. So the next number should be 5. Like that, previous two numbers should give, like if you want to see how it was like that. Same way, product of first two terms should give me the result as product as the third term like that. Okay, now let us read some definition. See what I have said now is a what to say. General principle or general basic knowledge for solving it. Okay, actual definition, let us just study now. A cyclic group is a group that can be generated by a single element. So, which means now if we have any one number of the group, for example, in the group we had 2, 2, 4, 8, 16 like that. See, 2, 4, 8, 16. Now all this number I can generate only with 2 now. 2, 2 square, 2 cube, 2 power 4 is 16 like that. So that is nothing but a cyclic group is a group that can be generated by a single element called the generator. So here this 2 is a generator denoted by G in this left hand right bracket. Every element of A in G is of the form G power n. Like I said, 2 power n for some integer n. If G is a generator for a cyclic group, we say that G generates G. So 2 generates all the numbers in this group. The group W4, comma, this multiplication, you can either consume star, and W4 is equals to 1 minus 1 I minus I. This is also that fourth root of unity. In this group, we notice that, see here, now I can say I minus 1, or sorry, 1 minus 1, I minus I. I can generate all these four terms with the help of I, only I. So anything to the power of 0 is 1. So I into I know that, see, we know that from the fourth root of this previous topic, like I said, I into I. When powers are same, it is what to say minus 1. Okay, so that's why I square will give me minus 1. Then I to the power of 1 will give me I. Now how I'm getting minus I with I cube? Now see here, I know I into I is equals to minus 1. So again into I cube I do. So into I do. So I into I is I cube. I into I is minus 1. Minus 1 into I is minus I. Okay, that's that I'm getting here. So thus every element of the group is an integral power of the element I. Hence this group W4 is a cyclic and I is a generator, that is W4 comma dot is congruent to I. Okay, this dot, okay, dot means multiplication. Now let us see to this example. Now I'll tell you how to find out the generator and all. It's not so difficult, it's very simple. So show that G comma star, whose multiplication table is as given below, is cyclic. So in this type, in this they have given this question like a table already. So have to show it is cyclic or not. Then first let me see here. See now, if suppose they have given this table or only they have given the letters, how to find the know that it is cyclic or not. First you will write A B C D E F, A B C D E F like this as it is. See, this thing will be as it is. First you will start A B C D E F, then you will start with B. Our best thing is just write A B C D E F like this, right? Then keep on writing the next term until F. A B C D E F, then B C D E F. उसके बाद you have to write A, then C D E F, then A B. Same order, just places are getting shifted. Then D E F, A B C, then E F C, same. So here starting with E. Now see here, E, A, C, then B. Sorry, this is the E, D, C, B, A, then F. How like that it will be continuing. So now, sorry, it is going like this, right? A, B, C, like, oh sorry. This it will go in like this. Okay, one of the other itself, all the terms will come. Always remember that. So here now F is there. After F what? F A B C D E. That's it like that. Now we can see that this is multiplication. Because of this binary operation, you can see that it is multiplication. So A into will give me A into B will give me B, A into C will give me C, A into, so you can see here when multiplying with A, I am getting all the elements as it is here. You can see here, right? See here, all the elements are as it is when I multiply with A. So I can say that my A is the identity element. Now how to find inverse? See, now since my A is identity, I know that A into A inverse should give me identity element, which is nothing but my A itself. So A into A is giving me A. Then B into what element will give me A? I can find out from this table itself. See, B in B, where I'm getting A, it's getting A. When I'm multiplying with F. So for B into B inverse. B inverse is nothing but F. So B into F is giving me A. So F is the inverse of B. Similarly, now see here for C, I have E. So when I multiply C with E, I am getting A. So for C, E is the inverse. Similarly, you can say that when I'm getting B into F as A, I can also say F into B is A. So for B, F is the inverse. For F, B is the inverse. Same for C, E is the inverse. For E, C is the inverse. Then for D, I have D as its inverse itself. So D into D, I'm getting D. So D is the inverse of itself. That's it. So E, like I said, I have already found for E and F like that. That's it. So I have explained everything. Now let us write in theoretical. From the table, we know that for all A comma B belongs to A. So I have to show it is a abelian first. Okay, cyclic group is nothing. First I have to show it is abelian or not. Then I have to say it has an identity element. It has a generator. How will we finding the generator and all? So before going to the generator part, let me first show that I don't think here we have to prove that is abelian or not, but still let us see what we have here. For all A comma B belongs to G, A star B belongs to A, means A into B belongs to A. Therefore, G is closed under this binary operation. Okay. For all A comma B comma C belongs to G, A star B whole star C is equals to A star whole B star C. Therefore, A is associated in G. Then the identity element A is in G. So the identity element in G is A. So every element of G has a inverse under star. That is, now see, B inverse is F, C inverse is A, D inverse is D, E inverse is C, F inverse is B. Usually, because of the cyclic thing, if B inverse is F, then F inverse is B. If C inverse is E, then E inverse is C. That's what it is. Okay. Then in addition, we have to say every element of G is of the form. Okay, now I have to see B into A will give me B. Okay, so now see here B into, okay, sorry, first let me take B into B, that is equals to B to the power of 1. I'm getting B. B square is something B into B. So here B into B, what do I have? B into B, I'm getting C. Okay, then B cube is nothing but B into C. Why I'm taking B into C? Because B square is C, right? B into B square is B cube. So B into C. Let me see. B into C is D. Same way, now B to the power of 4 is equals to B into D. Why B into D is D is equals to B cube, right? So B into D is E. Same way, if I could keep on giving B power 5 will become my F, B power 6 will become my A. So therefore, I can say that B is my generator. Here, B power 1 will give me B. B square is nothing but B into B. From the table, it is C. Then B cube is nothing but B square into B. That is C into B will give me D. B power 4 is nothing but B into B cube. B cube is what? D, right? See, like that. So B power 4 is equals to E. Same way, B power 5 is equals to F. B power 6 is equals to A. So I can say that B is a given generator of G. Similarly, F is also generator of G. Similarly, and then I have to check for everything. Just see now. C into, first I'll take C power 1, that is C. C square is what? E. Then C square is what to say? E, right? Then C cube. C cube is nothing what? C into E. What is C into E? That is A. Then C power 4 is nothing but C into A. So C into A is C. Now see here, C power 1 is also C and C power 4 is also C. If I try to take C power 5, that is nothing but C into A, I guess. That is again C. No, no, no. Yeah, C into CE. So it will be giving repeated values. I won't get B and D and that. So similarly, if I take for D also, that's the same case. But in F, I'll get okay. The uh, F power 1 is F. F into F square will give me E. Okay. So F cube, F into E will give me D. So like this one, if I do one by one, I will be coming back. Okay. For a simple way to understand is something but first letter. Okay. So see, either my last letter should be at the first, or the second letter should be at the first. Then aram say, or else yeah, or best thing. First letter should be at the last, or last letter should be at the first. You can see here it is F, and for B here it is A. Then most probably those two things will provide the generator. Okay, so therefore I can say that it is a cycle group. Similarly, now I have to prove that the group Z4 comma plus is a cyclic. Find all its generators. So now only they are given Z4 comma plus. So now what I'll do, I'll consider the elements of this Z4 first. Z4, like this I will do. So here what I'm doing, 4, it is 4 at 1, 2, 3, 4 will be there. But I'm considering 4 is equals to 4 as 0. So 0 comma 1 comma 2. Okay, then 3. 0, 1, 2, 3. So I'll write plus. Here it is plus. So there will be multiplying. Here we will do addition. 0, 1, 2, 3. 0, 1, 2, 3. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. Under this operations, first I have to say that from the table it is clear that Z4 is closed on the plus. So from this I can say that 0 is an identity element. Okay. Then I can also say that now see here 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, then 1 plus 3 is 0. How I am getting 0 is nothing but it is cycle, right? So since it is in cycle, so it's 1 plus 3 should give me the what to say second that next number. So it's like this. Wait, I'll show you. Like this it is going, right? So if I add 1 plus 2, I should get 3. If I add 1 and 3, the next element I should get as 0, which is 4 actually. But here 4 is equals to 0. So I'm writing 0. Understood, right? Then suppose 2 plus 3 is this. 2 plus 3 I'm writing as 1. Okay. 2 plus 3. How means? Now see here. 0, 1, 2, 3. If I'm getting 2 plus 3 as 5. Okay, what I'll do? 1, 2, 3, 4, 5 like that one by one I'll come. So here I'm getting 5, right? So simply what you do, just remember 1, 2, 3, 4. This you remember in mind. No matter what addition you are getting. So if you are taking 3 plus 3, that is 6, right? 3 plus 3 is equals to 6. Here 3 plus 3 I'm getting 2. How means? Now see here 1, 2, 3, 4, 5, 6. Where it is stopping 2. So I'll write 2. Similarly, 3 plus 2 is 5. 1, 2, 3, 4, 5. It is stopping at 1. Okay, it's like that, general thing here. Why? Because this 0 is nothing but 4, right? So I can write it as 1, 2, 3, 4. So like that is the addition. From this table, I can say, so now A dot B dot C belongs to A comma B comma C belongs to E. We know that A comma B comma C, three elements, I'm taking any three elements belong to C, such that A plus B plus C is giving me A plus B plus C. This associative property. Then I can say that 0 is the identity element, and we know that inverse of okay. Now 0 is the identity element. Now how to find the inverse of 1? So inverse of 0 is 0 itself. Inverse of 1 is, see where is 0? It's see here. From which term I'm getting? Because of 3. So for 1, 1 inverse is 3. 2, 2 inverse is equals to, here I'm getting 0. So 2 inverse is not 2 itself. Then 3 inverse, I'm getting 0 here, that is 1. Understood? 1 inverse is 3. Like I said, if I'm getting 1 inverse as 3, then 3 inverse will automatically be 1. and I know that 0 inverse is 0. So remaining you don't have to see also, you can simply write off 2 inverse is 2 itself. Then I'll say which is the generator. Now we can see here I'm using here 1 as a generator. How means, let me show. See this here, just read it out. It's about inversing. Then every element of Z4 is an integral power of 1, means 1 is equals to 1, 2 is equals to 1 plus 1. So they are writing 1 plus 1 as 1 square. So here because of the that what to say, plus is there, right, binary operation. So 1 square, instead of doing 1 into 1, they are taking 1 plus 1. Same way 1 cube, 1 plus 1 plus 1 as 1 cube. 4 is equals to 0, so 1 plus 1 plus 1 plus 1 is 1 power 4. So 1 is a generator. Then therefore this is cyclic, they'll do. Similarly you see here in addition, okay, have they repeated this again? Yeah, they have repeated this again. This page has repeated again, sorry for that. See, they have written here. Now what is this? 1 is equals to 1 comma 2 comma 3 comma 0. Now they are trying to find out if other thing is any other element is also a generator or not. So 2, then I'll take 2 plus 2, that is 4 is 0. So like that I'll take. Then 2 plus what to say, 1 plus 1, then 2 plus 1, 3 plus 1, 4 plus 1. Then 2 plus 2 is equals to 4 is equals to 0. 3 plus 3 is equals to 6. 6 plus 3 is equals to 9. I can almost take 0 to 4 is equals to 0. So see here, all the things. This if you write or not also, it's not fun. So 1 and 3 are generator of group Z4 plus 1. So see, 2 plus 2 will give me 4. It is equals to 0. So if I take 2, 2 is 2 plus 2 is 4. And if I take 2 square is 4, 2 cube is what? That will be 2 plus 2 plus 2 is 6. 6 will again give me 2. Like I said, 1, 2, 3, 4. So 2 plus 2 I got 4. Then 4 plus 2 is 6. I'll get this. Then again if I add 2 from 6, 6 plus 2 is 8. Will again stop at 4. So I'll be waiting only 0 comma 2 in this. If I try for 0 also, now see, so 0 plus anything, I'll get only 0, 0, 0, 0 itself. So I'm not getting anything in 2 and 0. But in 3 I will be getting. Now see here 1, 2, 3, 4. So first 3, it will be at 3 itself. Okay. 3 to the power of 0 will give me 1. 3, sorry, leave. 3 power 1 is nothing but 3. 3 power 2 is nothing, 3 plus 2, that is 6. So first I got 3. 6, how I'll get? 1, 2, 3, 4, 5, 6. So it will stop at 2. Then 3 power 3, that is 9. So how 9 will come? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is stopping at 1. Okay. Same way 3 power 4, that is 12. So 12 means 1, 2, 3, 4. 4, 3 are 12. So it will stop at 4. So I am getting all generators. So that's why I am saying 1 and 3 is my generator. Now Klein force group. So what is a Klein force group? That is nothing but a group G is said to be a Klein force group if G is an abelian group and each element of G has self-inverse. Okay, it has a self-inverse and an identity element as E. Okay, self-inverse is nothing but like how in previously I found out for now I can, let me just take one example. See now here if you can see here the inverse element where we have written for 1. Okay, see 1 inverse is 3, 2 inverse is 2, 3 inverse is 2, and 0 inverse. So in abelian group 1 inverse will be 1 itself, 3 inverse will be 3 itself, 4 inverse will be 4 itself. Okay, that you have to remember. If that property is satisfying, then it is an abelian Klein-Force group. Okay, a Klein-Force group is also an abelian group. You have to know that. We'll just take one example. You understood the definition, right? So now let us understand with an example. If A is equals to, this is a general what to say, question for Klein-Force group. Two questions will be asked. One is 1, 3, 5 and 7, or this question. So let us see this question first. If A is equals to E comma A comma B comma C, then show that this is a Klein-Force group. So here we will consider that A is equals to, this is on this set we define a binary operation as follows. So that star operation I am performing. So here E is nothing but an identity element directly because we can assume from that this itself. So only A, B, C will be my what to say, actual this considering terms. So now you can see here, E into E is giving me E into E will give me A. This is general, what to say, form in groups. So in beginning itself, we have seen that X into, that is formula is there, X is equals to E into X. So anything I multiply with E, so I won't, whatever I'm multiplying, only that itself will be my answer. So I can say that E is my, what to say, uh, identity element. Now see here, for A, I'm getting, so A into A inverse will give me, okay, E. So here, what is that element here? Let me find. So I'm getting E here. A into what? I'm getting A into A. So for A itself is the A inverse is equals to A itself. Then B, so see under B into B itself, I'm getting as identity. So B into B inverse is nothing but B inverse is nothing but B. So same way C inverse is nothing but C here. From the table, I can say that A comma B belongs to A, where A into B also belongs to A. So see, I'm not getting any extra additional term, the next or something. All the terms generated while multiplying A into A into all this thing B, I'm getting all A, B, C or E itself. So I can say that A into B belongs to A, therefore A is closed under multiplication this dot. For all A comma B comma C belongs to A. So now you have to do this. Simply write like this and say to them A comma A dot B and dot C is associative. Then you will say the identity element is G in every in A. So the every element of A has an inverse index, that is inverse of A is A, that is A inverse equals to A. Simply write off. According to the definition, you have to say that for A inverse is A, B inverse is B, C inverse is C. We find that for all A comma B belongs to A, AB belongs to BA. So once you find the inverse thing, the identity thing, the associative thing, the last thing left is for Klein-Foes group, that is commutative property. A into B is equals to B into A. So we can see that A into B is also equals to B into A. Well, let us take example. See, B into A is what? C. Then A into B. A into B is C. Okay, you can see that, right? I cannot take from here to here, from top to left. No, from left to right, I am multiplying, right? B, see, B into A is giving me C. So A into B is also giving me C. Understood like that. So therefore, it is an Klein-Foes group. That's it. Much more is not there for that. I'll also solve another the problem if they give 175 1357 after I finish this. Let me just complete this as soon as possible. So additive group of a modulo n is denoted by Zn plus of n. Okay. So additive group of one. So whatever n we have in the given question, Z. So they might give Z4 plus of 4 like that something. So that will be denoted displayed here. Okay, so what is this? Okay, first let me, yeah, it will start from here itself. So for example, n is equals to 6. Okay, so if n is equals to 6, z6 plus of n. Okay, so 3 plus of 6 is equals to 2. It's nothing but 3 plus 2 is equals to 5. So 0, see now 1, 2, 3, 4, 5. Okay, now see what I am getting, that is 5. Now 5 will be added with this term, what to say, previous term. So 5 plus 3. 5 plus 3 is what? 8. But 8 is equals to 2. How I am getting 2 is nothing but, now see here, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Now see here, I won't include my 0. So I'll, instead of 0, let me just write again properly. I should not consider 0 actually. So I'll write here 1, 2, 3, 4, 5, 6. Now see here, 8 is here, right? So 1, 2, 3, 4, 5, 6. Always consider that cycle. Okay, better I write off like this, right? That is more good. 1, 2, 3, 4, 5, 6. Okay, this is more easy to explain that. So it is starting from here always. See, 1, 2, 3, what the heck? 3, 4, 5, 6, 7, 8. So it is stopping at 2. So I'm getting 2. Then I got 8. Then I'll add 8 with that. See here it was added with 2. Then the result element will add with 3. Then that resultant element will add with 4. Like that, so on. If I keep on doing, I'll be getting 5, 2, 0 like that itself. So I'll say the operation table Z6 plus. Okay, how I'm getting, that's why they're just showing. This is not necessary to write in examination, but yeah, after this table you can just show here how 0 plus 0 is giving me only 0, 0 plus 1 is giving 1, or other elements to fill the paper. That's it. Now see here, same thing I'll tell you the trick, whatever I said. So it is plus, right? 0, 1, 2, 3, 4, 5. Then like I said, like this also and like this also, just in this direction, just write 0, 1, 2, 3, 4, 0, 1, 2, 3, 5. Then keep on writing according to this cycle 0. Now here I consider 1 to 6 for showing you how it is added. Instead of 1 to 6, just consider this 0. These are 0. Okay, so now we will start. So here it is starting with 1. So 1, 2, 3, 4, 5, 6, 0. Sorry, 5, 0. Then it is starting with 2, 3, 4, 5, 0, 1. Like that. You understood, right? Like so on, you have to write. That is what additive modulo. Same way if they are giving multiplication modulo. Same way. See how here, whatever the value we got here, I showed you. One by one, you will go like this and come the same way here also. You multiply and you get the values. One by one, again you will be cycling, cycling, cycling. Where it will stop, that is the answer. Same. Much difference is not there. Even in see multiplication, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So first you write 1, 2, 3, 4, 5, 6. But here you see 2, 4, 6, 1, 2, 3, 5. It is changing. How to do this? Now see here. 2 into 1 is 2, 2 2s are 4, so 4 3s are 6. Until 6 I write as it is. Then 2 into 4 is what? 8. Okay, 2 4s is 8. How for 8 I'm getting 1. Let me see that. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, let me consider in this 0 also. So if I consider 0, wait, 2 ones are 2. Okay, then now see here 8, right? 1 2 3 4 5 6 7 8. So I'll write 1. 2 5s are 10. So I'll start with 1, or I can start with what to say 0 also. 1 2 3 4 5 6 7 8 9 10. I think I have to start with 1 self. I think 1 to 6, will it come give me 1 to 6 or what? 1 2 3 4 5 6. So 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7. So okay, if I start with 1 2 3 4 5 6 7 8. Yeah, okay, now I got it, I got it. Sorry. So see here, it will go like this, right? Just include 0 in this. Why? Because it's 2 multiplication, already 2 is occurred. So see now, for each term I'll start with here. This is the starting. So 2 4s are 8 I got. So 1 I'll start. So just keep in hand 1 2 3 4 5 6 7 8. It stopped at 1. So I'll write here 1. Then same way 2 5s are 10. I'll start with 1. 1 2 3 4 5 6 7 8 9 10. It stopped at 3. So I'm writing 3. Same way 2 6s are 12. So for 10 it stopped here. Then for 12 it will be 10. This is 11. It's 12 5 like that. Same way for 3 also. 3 1s are 3. 3 2s are 6. 3 3s are 9. See, I'll start with 1. 1 2 3 4 5 6 7 8 9. I'm getting 2. So I wrote off 2. You understand? Same way, just multiply whatever the value in this cycle. Just try to write that one by one. Where it is stopping, you will get that values. Then this is permutation group. So consider a set A is equals to 1 comma 2 comma 3. The elements can be permutated or arranged in 3 factorial ways. How many number of elements? That much factorial, n factorial is a arrangement, number of arrangement, that is 6. So 1 2 3 2 3 1 3 1 2 then 1 3 2 3 2 1 2 1 3. I am just arranging, so nothing but, so see 3 digits, right? How can I arrange? So here I can write 1 2 times, here I can write 2 2 times, and 3 also. All these 3 numbers I can repeat here 2 times. Same way here also, all these 3 numbers I can repeat 2 times. Here also I can repeat 2 times. Okay, so how many times? 2 2 2, that is 6, like that. So the 6 permutations of the set A is equal to 1 2 3 are. So first it will be 1 2 3 1 2 3 1 2 3, first line. Just in second line you have to write all this what to say arrangements one by one. That's it. That is that what to say permutations. Sometimes they might also give that in permutation such that no element is in proper in its original place. That is nothing but dearrangement in that. So that will be like, see, this won't come. This is correct. This is also right for that. This is also nice. This won't come. Why? Because 3 is in its original place, and here also this won't come. Why? Because the 2 is in its original place. So if they have to, if they say that no element is in original place, then this this three things can come in that. Okay, if one is here, then 3 2. That's it. Nothing. Sorry. Oh, even this won't come. Why? Because one is there, right? So here I can write 3 one time, 2 one time. So if I write 3 1 2, if I write 2 here, 3 1. Okay. See, 3 1 2. I'll just write 1 2 3. So here I can write 2 3 1. Okay. Here I cannot do 3 2 1. Why? Because if I do 3 2 1, 2 will be in its original place. No, here 1 3, here 1 2. So that's it. Only one time I can do. You can see here, if here 1 is there, the other two elements are coming. If here 2 is there, the other two elements, like that. That is also one type of thing they'll ask. I'm just clearing it here. So then subgroup. A non-empty subset H of a group G is called a subgroup of G whenever H itself is a group under the binary operation G. Suppose we have 1 to 9 and we also have 1 to 3. This group is a subgroup of this. That's what it is. Okay, denoted by H less than equal to G. Example, H is equal to 0 to 4 belongs to Z of 6. Z of 6 is nothing but 0 to 0 to 5, where 6 is equals to 0. Okay, H comma plus is a subgroup of Z6 comma plus. Okay, see, usually we denote a group as this, right? Only Z6 also you can write in caps, or else Z6 comma whatever the operation we are doing, either plus or multiplication. Okay, we don't take subtraction or division here. Okay, note every group is a subgroup to itself. Then coset decomposition of a group. This is just theory part. No? Okay, I'll solve that problem on that. What is that subgroup also? Okay, first let me and we also have that Lagrange's theorem also. Okay, let G comma star be a group and H comma star be a subgroup of G. So this is a group. This is subgroup of this group itself. For any A belongs to G. So for any A element A belongs to this main group, let A star H is equals to A star A into H such that H belongs to H. Okay. A star capital H is nothing but A into one small h, some element H we are saying. So H belongs to capital H. That's the thing. Then H star is nothing but H into A star. Here same way H is belongs to H. Same thing I'm writing. So then A star H is called left coset of H with respect to A. Then H into A star is called right coset of H with respect to A. In the sense, now see here, G is the main group. My subgroup is H. Okay. Now A belongs to G and B belongs to H. So if I'm doing A into B, see, main actual group element into subgroup element. So then where is this is the subgroup element, right? So I'll say that this A is the left coset of B. Okay, A is the left coset of B. If I do B into A, so this is the subgroup element B and A is the main group element. So B into A. So subgroup this A is towards the right of the subgroup element. So I'll say A is the coset, right coset of B. That's it. Then for the group G is equals to Z12 comma plus and the subgroup H is equals to 0 4 8 of G. See, Z is nothing but 0 to 11 where 0 is equals to 12. In previous sums we saw, no, according to that I can say. Then H is 0 to 4 8 of G. Find all the left cosets of H in G. Also obtain the corresponding coset left coset decomposition of G. First, let us see. Z12 is equal to 0, 1, 2, so on up to 11. Left coset of H with respect to A belongs to Z2, Z12 is A plus H. which is nothing but A plus H such that A belongs to H. So since here in the question they gave Z plus, right? So we know that in here, see, A star H is equals to A into one small element H from that G. One by one I have to take. H belongs to capital H. So here plus is there, so I'll take plus. Nothing but A plus 0, A plus 4, A plus 8. So this is my actual, what to say, left coset element. So how it will be? So one by one. In place of A, I'll be substituting 0 to 11. See here, they have did everything they have to do here. So 0 plus H is nothing but 0, 4 itself. 1 plus H. See 1 plus what? 1 plus 0, 1 plus 4, 1 plus 8. 2, 5, 9. Then 2, 6, 10. So on if you do. So whatever, see here, 10 plus H, 11 plus H. So we note that out of 12 left cosets listed above, only 4 are mutually disjoint. They are 0, 1, 2, 3. Others are identical with here, which what it means now see here. Here I am getting a few repeated terms. Like I said, in addition, this cycle will be followed, right? You will start from 1, 2 and end with 12. So if you are getting any number more than 12, so just count from here 1, 2, 3, 4. Suppose I am getting 20 as my answer. So what will be 20 minus 12 you have to do. What is that? 8. So you will write off 8 at that place. Okay. Let us see if anything. Okay. So see here 12. Okay. I don't have that. 11 plus 8 is 19. See 19. 19 minus 12 you have to do. What is 19 minus 12? 7, right? So see here 12 plus 8. 12 plus 8 is giving me 7. Understood, right? So what it's saying is only first 4 elements are distinct, which means all the elements of from 1 to 11 I'm getting under this first to 4. See, in each of these 4 places nothing has repeated. So but it has also covered all the numbers like from 0 to 11. See here 0, 1, 2, 3, 4 is here, 5, 6, 7. Okay, 7 is here, then 8, 9, 10, 11. So this much I'm considering. Okay, that's what they are saying. Same way if they had asked us to find the left coset, both even the both are same. Left coset or right coset we do. This is left coset. Right coset means H plus, like this will be, which is nothing but same only, no. So H plus 0, this will be same. So both left and right cosets, the answers will be same. So we can also write like this here is equals to H plus, like this, makes no difference. Okay, the left coset decomposition of Z12 comma plus with respect to H, Z12 plus 1 is equals to, I think here with respect to H is 0 plus H union, 1 plus H union, 2 plus H union, 3 plus H. Why? Because see all the elements which I have under the coset, if I do union of this 4, then all the numbers will get added and will be adding. So it is nothing but 0 to 11. That's why I'm writing it as H, this union plus this union plus. So note that symmetric group that consists of all the permutation of set of n elements denoted by Sn. Suppose H is a subset. See, this symbol means a subset symbol. Okay, H is subset of G, and if G mod G is equals to 4 factorial, is nothing but 24, means total number of elements under G is 24, and H is equals to only 4. Then there are 24 by 4 is equals to 6 left coset of H in G. Okay. So here see 4 coset. So 24 by 6. So okay, left coset is equals to H in G. So let G is equals to S of 4 for alpha 1, 2, 3, 4. Find the subgroup H is equals to alpha. Determine the left coset of H in G. So the given is H is equals to S4, a symmetric group of 4 order. Now what will be the number of subgroups? Cosets is nothing but 4 factor is what? 4 4 the 4 into 3 into 2 in, okay, 3 2 is the 6, 6 4 the 24, 24 by 4. 24 by 4 is what? 4. So I should have 4 cosets. So it is nothing but, see here how this is arranged. Like I said, each number should not be in its original place. Okay, first you will take, okay, just dearrange it. Okay, 1 2 3 4, then 2 3 4 1, 3 4 1 2 4 1 2 3. One by one you will just write like how normal table we used to do, right? One by one that numbers will be right. So 1 2 3 4. In second one 2 3 4 1. Then 3 4 1 2. Then 4 1 2 3. That's it. Since h is a subset of g is equals to s4 and g is equals to 4 factor, then is 24 and mod h is equals to 4. Then there are 24 divided by 4 is equals to 6 left coset of g. Oh, okay, it is 6 actually. So now, okay, 6 coset. How means, I got four ways I can arrange this first in general without repeating any number, without repetitions. I can arrange it 4. Now see here, h is equals to, so here what they have done, 2 1 4 3, right? 1 2 3 1 2 3 1 2 0. Same, see now I have here 3 2 1 4 4 3 2 1 1 4 3 2 and 2 1 4 1. Just what you're doing, the possible ways of all the things. So this should not repeat. Sorry, this will also repeat 2 1 4 3 plus. Then what I'm see, okay, it's okay, I understood what you have to do. So this is 2 1 4 3, right? The next, first write this here. The next element will be, just put this at the last, right? 1 4 3 2. See, 1 4 3 2. Then what you will do, now you will put 1 at the last, 4 3 2 1. Then now you will put 4 at the last, 3 2 1 4. Okay, done. Same way here, 4 2 3 1 was there, right? That will be last. Now what I'll do, I'll put 4 at the last. Then what will be 2 3 1 4. See, 2 3 1. Where is that? 2 3 1 4. It should come. Oh, why is it coming here? 2. Okay, just do it here. Okay, I see here 2 4 3 1 2 4 1 3. Do it like that one by one. I'm sure that you will get all different this itself. 1 4 2 3 1 4 2 3. So just what you have to do, no, what I'm saying is, so since it is 4 elements are there and 4 factorial is 20, 4 square. 4 square is nothing but 16. So 4 4 2s are 8, 8 2s are 12, 12 plus 2 is 16. All these are different arrangements. Okay, so you have to just write like this. Okay, then here again h of 1423 is equals to same thing they have written, 1 2 3 4 1 2 3 4 1 4 2 3 1 4 2 3 1 2 4 3 4 2 3 1 2 1 4 3. I can write it as 1432 here. Make it 1432. Just nothing, that's it. You understood, right? You just have to write the numbers in such a way that it's not repeating, that's it. If H is a subgroup of a finite group, then for all A belongs to G, prove that A plus 1 is equals to H. A plus 1. Since A into H is equals to A into H, as that H belongs to H, normal form, it follows that mod AH is less than equals to mod H. A into H is less than mod H. Mod H is the total number of cosets. So if AH, mod AH is equals to mod H, and we have A into H of I is equals to A into H of J, where H of I and H of J are different elements of H. By left cancellation in G, we get that Hi is equals to Hj. In the sense what? Suppose you have A into some constant B, which is equals to A into C. So here left cancellation, B is equals to C. In same way, I have H into A into H of I, A into H of J, A cancel. So that, like that is saying Hi is equals to Hj. Okay, so H is a subgroup of that finite group, and for all A belongs to G, then prove that A into H is equals to H. So what I'm saying is, see, all the elements if I take from this left cancellation property, I can say that H1 is equals to H2 is equals to so on up to HR, where each element of H is equals to, which is equals to H. So what I'll say, everything is H, 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 H. So no matter what element I take, that will be is equals to H itself. Okay, that's it. It is saying nothing else. Then Lagrange's theorem, a very simple thing. After this, I don't think much questions are left. Then it will complete our every complete fifth module syllabus. So if G is a finite group and H is a subgroup of G, so G is a finite group, so numbers are finite. It's not infinite. So 1 to suppose n, and H is a subgroup, suppose 1 to m. Okay, then the order of H divides the order of G. Now here, first you have to remember, first you have to say statement. This is the statement. What there is a state Lagrange's theorem. So what you have to say first, you have to talk about one group that is G, and you have to talk about one group that is H. Then what you will say, if these two groups are there, then order of this will divide order of this. Okay, so this is the statement. Understand this one. That's it. Now proof. Since G is a finite group, we can also say that, and H is a subgroup of G. Therefore, we can say that H is also finite. Why? Because from this finite group G itself, now we will take elements and put in H, subgroup H. So now number of cosets of H in G is finite. That also we will say H is finite. If H is finite, then number of coset in H. Like I got in this previous sum over here, where see number of cosets also it is 4, right? That is also finite. Okay. Then what I'm saying, let H into A1. So I'm writing all the right cosets. H into A1 into H into A2. I don't know how many numbers elements are there in G. So H into A1 comma H into A2 comma H into A3, so on up to H into, you can take AN or AR. So here I have taken AR. Okay, they are saying these are the right cosets of H. Right cosets of H in G, inside G. Inside G itself we will get all this. Then by right coset decomposition of G, we have G is equals to, just write off all these things again. A union will come. Instead of comma, just put off union. Okay. G is equals to H into A1 union H into A2. Like I said here, see here, what is that statement means? If cosets are there, right, then actual coset G from right decomposition is nothing but, see, whatever the numbers are distinct cosets are there, that union, this union, this union, that union. That's what they are here also they are doing. H in A1 H into A1 union H into A2 union H into A3 union. So that what I am doing, same thing, just write a composition before each element. Now union will become plus. First comma was there, comma becomes union, then union becomes 1, and before one composition circle will come. Okay, just remember this thing. This was comma union composition H into A plus. Okay, then what you will say, composition we know, but you will write from that what to say coset decomposition of coset, from that coset thing, composition of H into A1 is equals to composition of H into A2 is equals to composition of H into A3, so on up to composition of H into AR, which is equals to 0 into H. The composition of H, sorry, not 0 into H, composition of H. Okay, then what you will do, you will substitute each place. So here H of 0 was there, right? So instead of H of A, you will only write H, only H, only H, so on up to H. So see here, you can see that 0 composition H plus plus plus. So n r number of times, n number of times this is being added. So I can say that n into composition of H, or in this case they have taken r, so I'll take r into composition of H, which is nothing but r is equals to composition of G divided by composition of H. Only this thing I am sending down. So I can say that this shows that order of H divides order of G, which is nothing but G is divisible by this. That's it. We have to say a proof for Lagrange's theorem. Now, under Lagrange's theorem, two questions are there, which can be asked in your examination. We will see that. Let G be a group with subgroup H and K. If G is equal to 660, okay, and K is equal to 66, and K is a subset of H and H is a subset of G. Okay, see, first I have G, uska subset is H, and subset of H is K. So here they are saying in K there is 660 elements. Okay, and array and in K they are saying this is not 12, it is K. In K they are saying it is 66 elements. So they are saying what are the possible values of H. Since they are saying possible value, be smart enough to understand that possible value is more, how many values. So it can be more than one. It can be only one also, but it can be more than one. Okay, so now let me say by Lagrange's theorem, H must divide order of, see, subgroup will divide the order of actual group. So G is divisible by H. Then since K is a subset of H, then H is also divisible by K. Okay, I'll assume this. Well, I understand H must divide G and K is equal to 6 must divide H is equal to 11. Also, we have that each thing is not equal to each other. So G is not equal to H, H is not equal to K. Therefore, see, so what I'm saying, now see here, what I'm doing, G, order of G, right? Order of G divides order of H. Okay, so I don't know what is my H now, but I know order of G is nothing but 660. 660 divides order of H. Let this be some, what to say, constant A1 you can take. Then I also know that order of H can be divided by order of K. Okay, order of K, which is nothing but order of H can be divided by 66. Let this be is equals to A2. So what I will do, I'll send this, what to say, H here. Okay, so 660, here 660 is equals to order of H into Q1. For some integer Q1 is greater than 1, and H is equals to 66 into Q2. Okay, for some integer, see, I'm just sending H here, so 60 is equals to A into 1. I'm just sending 66 here, so H is equals to 60 into that constant. Hence 660 is equals to, now see here, what I have 66 is equals to H into Q, but I got H value as Q2 into 66, which is nothing but 66 into Q1 into Q2. So now what I'll do, I'll bring the 66 in the denominator. If I bring like this, then I'll have 1s, 10s. So here they are saying Q1 is equals to 10, Q1 into Q2 is equals to 10. Now we know that which two numbers will give me 10. Okay, Q1 into Q2 is equals to 10. So there are only two numbers which will give me product as 10, product of two numbers, that is 2 and 5. So I can say that either Q1 is 2 and Q2 is 5. So what I'll do, so this equation I had here, right? Let me just erase here. See, now I had this equation, right? So in this equation what I'll do, one time I'll put the value Q1 as 2. Okay, so if Q1 is 2, 660 by 2 is what? 330. Then I'll put Q1 as 5 now. If I put it as 5, then it will be 5 ones are 1, so 160 is there. It will be 1s, then 15 is there, so 3 is there, then 2, 132 I guess. See, yeah, 132. So the possible values of order of H is either 330 or 132. If you see now, we can say that 360 can be divided by 330, that is into 2 times. Then, okay, now see, 330 can be divided by 66, that is 5 times. Order of K, H of order of H should be divisible by order of K, right? If H is 132, it can be divided by 66, see, 2 times. So divide by 60 2 times, and 660 can be divided by 132. How means 5 times. Simple. That's it. Okay. So if G is a finite group of order n, and G belongs to G, A belongs, okay, and A belongs to G, then A power n is equals to E. So they are saying if G is a finite group of order n, so order of G is equals to n, they are saying, and here A belongs to G, then A power n is equals to identity element. Okay, so let composition of A is equals to M, then A power M is equals to E. Okay, we know that if G is finite, then order of A is also order of A divides order of G. So here this is a subset I am considering. So order of A will divide order of G. which means M must divide the order of G. That is N is equals to K into M. So in the sense how I got this is nothing but order of G divided by M is equals to some constant K I am taking. So order of G is equals to order of G what they have given as N. So N by M is equals to I am some constant K, some value. So N is equals to M K into M, where K is a positive integer. Hence A power N is equals to A to the power of Km. So instead of N I am substituting Km, which is equals to A to the power of M whole to the power of K. So here I showed that A power M is E. So this A power M is equals to E is coming here. So E to the power of anything is E. Why? Because it is an identity element, right? So E to the power of K will give me E itself. That's it. How I'm okay? How here E to the power of what to say K is equals to E? I'm considering like see now here A to the power of N is equals to E. Anything to the power of M is equals to E. Okay, so here I'm considering this E as something to the power of M will give me E, where E belongs to G like that. Okay, and if H and K are subgroups of a group G, prove that H intersection K is also a subgroup of G. This is a model paper question. If and also you have to say H union K is a subgroup of G. Now see here, this is a main group G, and two subgroups of G are there. One is H and one is K. Okay, so for example, 1 to 10. H is suppose 1, 3, 5. K is suppose 2, 4, 6. Now prove that H intersection K. H intersection is what? 1, 3, 5, 2, 4, 6. If I do intersection, I will get 1, 2, 3, 4, 5, 6, which is again a subgroup of 10. So I can take this as a subgroup, right, from 10 actual group G. Under 1 to 10 only it is coming, right? So I have to prove that in words. That's it. So let G be a group and H and K are subgroup of G. There are any A comma B belongs to H intersection K. So what is saying A comma B belongs to H intersection K, such that A belongs to H. A comma B belongs to, first I will take H. A B belongs to H, then A B belongs to K. Okay, then therefore A into B inverse belongs to H and A into B inverse belongs to K. Why? Because if H is a subgroup of G, then A into B belongs to H, A into B belongs to H, okay, and A inverse will belong to H. So A inverse will also belong. Why? Because now see here, previous values we knew that A into some inverse element which is belong to this here will give an identity element, and that A inverse is also nothing but same element within that given set. So I can say that that inverse element also belongs to that particular group. So that's how what I'm taking. First I'll take let A comma B belongs to H intersection C. So that A comma B belongs to H, A comma B belongs to H. Then I'll take once same thing I'll write again. Instead for B I'll put inverse. Then for A I'll put inverse, which implies that A into B inverse belongs to H intersection K. Okay. So I derive that A into B inverse belongs to H intersection K. Hence H intersection K is a subgroup of G. That's it. A simple thing you have to write. Now consider the symmetric group S3 and two of its subgroups H is equals to P0 and P of 3, and K is equals to P0 and P4. So this is 0, 3 and this is 0, 4. Then H union K is equals to P0, P3, P4. From multiplication table for S3, we find that P3 into P4 is equals to P1, but P1 does not belongs to H union K. See, under union, I don't have what to say 1. See, I have only P0, P3 and P4. Here also I have P0, P3, P0, P4. But if I'm doing for union proper thing, that so union what you have to do, okay, just take 0 instead of P0, P3, just take 0, 3 and 0, 4. Okay, if you do union, what you are getting 0, 3 and 4. Okay, this is now H union K is equals to 0, 3, 4. But from that what to say, multiplication table, we know that, now see here, P3 into P4. So this into this, what is the 3 4 the P3 into P4 will give me P1 in the sense 0, 1, 2, 3. Suppose this is P3, this is P4. If I multiply 2 into 3, I have to get the next element, right? That should be 0. That's what it is. See here, like I said, 1, 2, 4, 1, 2, 3, 4. So what is here 3 into 4? That is 12. So if I have, see, where 4 is equals to 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my 12 is stopping at 4, which is nothing but 0. Okay, so here 0 I'm considering as P1. Okay, just I'm saying, okay, in this it is belonging to 0, but according to this what to say, P1, P2, P3, P4, if I take P1, P2, P3, P4, so product of two elements will give me the next element. In a cycle, the next element after P3 and 4 will be P1 itself. So it is P1 I don't have here in this union. Yeah, that's what they are saying. That's it. Like this, you can say that uniform. So, but not every time it is. See here, here you can show that it is not close under the product of permutations. But sometimes it can be, but sometimes it cannot be. So it is not a subgroup. So union of two groups need not be a group subgroup. Okay, prove that H is a subgroup of G if and only if all A comma B belongs to H. We have A into B inverse belongs to H. Suppose we just have to write this series. H is a group, subgroup of G. Then H itself is a group. So see now, I have G is equals to some group, like table I'll draw. Then H is also a subgroup of this. But this subgroup, it is a subgroup of G. But if only I'm talking about H without having any relation with G, then this itself is a subgroup. And this itself is a group in itself. Okay, take any A comma B belongs to H, then B inverse belong to H. How means? Now see, A comma B belongs to H. A into B belongs to H. Now A into some inverse will belong to H. How means? Like I said in the last time, I'll have E A B C, E A B C. So I knew that in that what Klein-Fo's group, A into A is A inverse. So A inverse is A, which is belongs to that group itself. So that's what I'm saying. B inverse belongs to H, so that A into B inverse belongs to H. Conversely, if for all A comma B belongs to H, then A into B inverse belongs to H holds. A into A inverse belongs to H, taking B is equals to A, like I said. Okay. Thus, E belongs to H. So I know that any term into its converse will give me identity element. So I'm saying that A into A inverse is equals to E, which belongs to H. The same condition can be applied to E, and A yields E into A inverse is equals to H when H is equals to where H belongs to H, which means, now see, first they took E belongs to H, done. So now what they are taking, same condition they are applying for A. Suppose here in now I had A into B, I took B inverse, then I made B as A. Now here I have A into A inverse, right? So now I am taking E as A. A is equals to E. So instead of A, I am writing E. E into A inverse will give me. So if E into A inverse belongs to H, then A belongs to H. In the sense, let me tell you properly. So A into A inverse belongs to H, which means E belongs to H, right? So E is also there in this group H group. E is also there. A is there. A inverse is there. E is also there. Now these two elements are there. Now what I am doing, I will group this E into A inverse such that it belongs to H. Okay. Also, A is also belongs to H. That's what they are writing here. Thus, A inverse belongs to H for every A belongs to H. So, for each A belongs to H, it itself, so self number itself is the inverse of itself that we are proving here. Since B belongs to H, we have B inverse belongs to H. Therefore, A into B inverse of whole inverse, that is A into B, which can be written as like this, belongs to H, that is A into B belongs to H. Thus, H is uh, Law also holds for all elements, H is a subset of G. Okay, this thing you have to just write normal cherry, and you have to do. So I hope I have explained all these questions properly to you, how, where and what is happening. Easy part was, see, suppose this question is not asked, you know how to solve this question, right? Very simple. Intersection wala and this 660 and this wala. Very simple. And Klein's, what is the Lagrange series also easy. Klein-Foss group, additive modulo, multiplicative modulo, all that is very easy. So I hope I have explained it properly. So I can just only say all the best for the exams. Study well.
Can I please ask you to subscribe? That's all we want, man. Just press subscribe.